Berkeley, and he'll be telling us about the persistence of long-range correlation.
Thank you very much, Ganesh. Is this okay? Is this working? Okay. And thanks very much to Kavita and Takis for the invitation to speak here. It's a real pleasure. It's a real pleasure to address this audience. Let's see. Did I get stuck? Okay. All right. Not a good idea. Sorry. Especially when you're being filmed. All right. Okay. So this is the work of my student Balas Ogus. He's I guess, relatively new student, and like all smart students, he's enjoying his spring break in Berkeley. This is our spring break week, so I get to give the talk instead. This talk is related to networks actually in multiple ways. Maybe I'll say that before I get into it. It's motivated by the empirical observations of Walter Willinger and his co-workers, which sort of set going the trend for the analysis and study of long-range dependence in network traffic. So in that sense, it's connected to networking. It's also the basic result is a result about renewal processes, which is new. So renewal processes are a standard modeling tool that we use in various kinds of network models. So that's another sense in which it's sort of appropriate for this forum. In many ways, though, the talk is also information theoretic in character. So it involves ideas like entropy and entropy density, etc. Now, we're all probabilists, so I'm sure we all have enough familiarity with it. But possibly we don't think about it as much as information theorists do. So the way I'm going to structure the talk is going to start out by sort of introducing some basic information theoretic facts related to data compression. I'll say everything that one needs to know as background. Then I'll present the aims of the talk and get into the actual details. So what I'll start out with is discussing the entropy rate of a stochastic process. Now, there's not too much that's technical in this talk. The process is going to be discrete time and finite state valued, so rather nice to think about. So the process is called x sub n. And script x is the state space. I'm going to assume that the process is ergodic. So let's use this notation, standard notation, for the joint distributions of, say, n samples. So this quantity is what is called the entropy. I'm pretty sure everybody is familiar with this, whether you work in information theory or not. So the key trick here is, fascinating thing about this definition is that you take the law of the process, that is p of x1 through xn, and you evaluate the law at the sample of the process. It's a rather mysterious thing to do if you didn't realize it was natural. And then you take the expectation of that on a per letter basis. That's the word that people use in information theory. And this expectation has a limit, and that's what's called the entropy rate of the process. The reason it has a limit is that there's a natural subadditivity in here. If you expand that joint distribution as a product of conditional distributions, you get this expectation as a sum of expectations, and the expectation of the conditionals actually decreases, so you get this limit. Logarithms are to base 2, that is traditional in information theory, but it's not particularly important to worry about that in this talk. So a standard notation for a sequence of variables is x1 through n, x1 through xn, so x sub 1 through n. Then you can in fact evaluate the entropy, or at least write this formula for the entropy. It's the conditional it's the expectation of the log conditional distribution of a sample given the entire infinite past. This is a natural consequence of this fact that the conditional entropies are decreasing. And then the ergodic theorem tells you that if you take a running average of these sort of conditional entropies given the infinite past, then it converges almost surely to the entropy. So these are some basic facts about entropy rate that I need to sort of load into our brains. Next, I'm going to tell you a little bit about data compression. Data compression is the process that is used widely. We all use it whether we know it or not, and when we work with computers, etc. And it's a process of trying to save on the amount of space or time that you use for representing real-world signals. Basic idea is the common currency is bits. So when we take a sample from the process, we try to represent it in an efficient way, some efficient way as a sequence of bits. The set of sequences of bits of arbitrary length is traditionally denoted like this. This is a computer science notation, shows up in logic also. Familiar with that? So what a compression code is a mapping from some block length of the source. So we think of the xn process as being some source of signals or some image or something like that. We represent the samples by binary strings of variable length. So this would be called a variable length code.
Is there a star missing?
Sorry?
Is there a star missing?
There's a star missing. Thank you. Yes, first typo. Okay. Sorry about that. That's very important, isn't it? Yeah. Okay. Was that? Thank you for noticing that. Yeah. Okay. So it's a mapping to sequences of variable lengths of binary strings, and we also need the property somehow that as you run along the binary string that you receive at the receiving end, you should be able to recover what was intended to be sent. So that's captured by the prefix-free property. That is, you're able to parse the string as you go along and figure out what was sent. So prefix-free mapping is one that has that property. So the image of x1 through n is called the code word, and this is kind of confusing actually, and to tell you the truth, it confused me for a while before I figured it out, because the word code is used quite a lot in information theory for two different things. So in Francois' talk, for instance, the code there was a channel code. This is what is called a source code. It's a data compression idea. Let Ln denote the length of the code word for the sample x1 through n. One of the basic results to get the theory off the ground is what is called Kraft's inequality. So Kraft's inequality is what you see there. The way you understand that is it's sort of telling you that if you want the prefix-free property, the binary strings that you use have to be at least as long as something. That's roughly how you think about this, because it's telling you that since the ln of x1 n comes in the exponent with a negative sign, it means that the ln's have to be reasonably large in order for you to be able to satisfy this inequality. So it's telling you can't do too much in effect. Now the proof of Kraft's inequality is actually rather straightforward. So it's encapsulated in this picture. The red dots you might think of as, there are 9 of them. You might think of them as these pairs of x's from a x of size 3. And what I have there is basically a binary tree. The node at the top you can think of as a root, then you branch to 0 and 1 and branch downwards. So in effect what you're doing with the prefix-free code is you're choosing a pattern of say 9 red dots in this tree of depth 4, and you want to make sure that no red dot is on a path from the root to another red dot. Now it's natural to associate weights to the nodes at different depths, which are like 2 to the minus the depth. And you can just see by looking at this picture that if you sum up those quantities, you can't get more than 1. So that's Kraft's inequality. This is basically a fundamental result in information theory. Please feel free to interrupt me if you have any questions. All this is just setting the stage before I get into the main meat of the talk. Now here's another result which is basic in information theory. This is not as widely known, and it's going to be important for what I say, at least to motivate what I say. It's due to Andy Barron in his PhD thesis, and also used by Paul Shields, I think. It's not really formally in the literature, but it's known as Barron's lemma. It's not too hard to prove, actually. So let's take a sequence of positive constants which has this property, that is the sum of 2 to the minus cn is finite. So to be concrete, you might think of cn as being something like twice log n, for instance, log to the base 2. Then you get the sum of 1 over n squared. That's clearly finite. So that's roughly the scale on which you want to visualize cn. Barron's lemma says the following. This is for any prefix-free code. Basically connects data compression to the characteristics of the source that is being compressed. So irrespective of what prefix-free code you use, and in fact for each block length n you can use a different prefix-free code. So for each n you have a different code, but it has to be prefix-free. You look at the sequence of random variables L sub n of x1 through n. They have to be lower bounded as random variables by minus log this. This is the conditional probability of x1 through n given the infinite past. Good Lord. Sorry. Should I allow connections? No, probably not. Okay, how do I kill this thing? All right, there you go. Okay, so you want to think about that p of x1 through n given the infinite past as a product of p of x1 given the infinite past, p of x2 given its infinite past, etc. So it's really like a running sum. and you have this, this lower bound. Just stare at the statement. We'll see it for a couple more clicks. Oops. Oh my God.
Security alert. No.
I have to close it?
Did you put the X in the corner? Upper left corner of the security box.
Left corner?
Right corner. Upper right corner of the box.
Okay.
Higher.
The X sign there.
But I can't, it doesn't go.
Okay.
Oh, hit the OK.
Hit the OK, all right. So goodbye, computer. All right. There we go. Okay, so if you stare at this, what you see is that you get this lower bound for your ability to compress on a per letter basis.
Cancel.
I've never had this happen before, so it's really weird.
Your email open?
No, I have nothing else open. This is very strange, isn't it? Ah, wireless, that might be it. Thank you. Disable wireless, that's a very good idea.
This is a networking session, you know.
Oh, that's what it is, yeah. Right. So it's a networking talk in more ways than I anticipated. Right. Okay, that's gone. Thank you very much. Yeah, great. It's good to have people who know what's going on. Okay, so Barron's lemma tells you this. Sorry?
What's the relation of Cn to the sequence?
No, you just pick any arbitrary sequence of numbers, Cn. They're just integers. The only point is it's giving you a kind of lower bound. And you cannot, in effect, it says that the lengths of the prefix-free code that you use cannot get much smaller than what the entropy is telling you on a sample by sample basis on the average, so to speak. That's how you want to think about this. Well, eventually, almost surely is a precise sense. So this is a statement. I'm going to prove the statement in the next slide, so we'll understand where it comes from. But a consequence of this, of Barron's lemma, is that the lim of ln x1 through n divided by n is lower bounded by the entropy. And this is a statement about random variables, so it's stated almost surely. Now, this is actually telling you something conceptual. Oh my God.
Oh, not this one.
Oh, crap. Something is really messed up here.
Just click on the screen so that you give focus to the PDF window and then you can use it.
Oh, it's back here again. Thank you. Okay, let's hope this kills it.
Just click on the PDF window, then it will have focus and you can ignore all that.
What do you want me to do?
Well, it's fine now. But
All right. Okay, so let's see. So let's try to get back in the stream of things. So this is Barron's lemma, and you can see from this from the statement of the lemma that you get the consequence that's down here, and that has a conceptual meaning. It's telling you that if you take a sequence of prefix-free codes, you cannot do better on a per letter basis than the entropy on a sample path basis, right? Now, this is traditionally called a source coding converse theorem or converse source coding theorem. It's called a converse theorem because it's telling you something that you cannot do. It's giving you some kind of bound on what you can do. And a direct theorem is a theorem that tells you something that you can do. That's the usual language. And I call it a first order theorem because it's sort of at the law of large numbers level. So it's on the average, it's telling you that you can't do better than the entropy. Here's a proof of Barron's lemma. It's not too hard. So let's look at the event that the ln of x1 through n is small in terms of this conditional log conditional density minus Cn, conditioned on the infinite past up to time 0. So the next line basically writes that out as a sum because everything is discrete. You can sum it over all possible samples x1 through n conditioned on the infinite past. So, but the condition itself tells you that you get the upper bound in the following line. You pull out a 2 to the minus Cn, and what you see there is amenable to Kraft's inequality, so you're done. Now, we've assumed that the quantities on the right-hand side sum up to something finite, so Borel-Cantelli brings you home after you take an expectation on the left. That's basically Barron's lemma. So what Barron's lemma now allows you to do, in effect, is it allows you to convert problems about the behavior of these prefix-free sequences of prefix-free codes into things that are intrinsic to the source, because they are now sort of described in terms of the log conditional densities. So I look at Barron's lemma, I subtract n times the entropy from both sides, and I get this statement, eventually almost surely. So if I want to do something that is somewhat more refined about how far away a sequence of prefix codes is from the entropy rate, it's enough to look at sums of IID variables. No, well, not IID, but sums of basically from a stochastic process, right? So what you can then do is, for instance, do the following. Suppose that you had a process that was sufficiently fast mixing that you were able to sort of prove a central limit theorem for these kinds of functionals of it. Then you could get essentially a second order source coding theorem. So under suitable conditions, you can show then that at the square root of n level, the left hand side is bounded below by a Brownian scaled Brownian motion. And a precise theorem of this sort was put in the literature by Yanis Kontianis in 1997. So called a second order converse source coding theorem. Now there's some subtlety here actually which is relevant to my talk, which is that this is telling you something at the level of the conditional distribution given the infinite past. But if you want to do direct theorems, somehow the code that you're using does not have access to the infinite past. It can only work with the block that it sees. So it has to somehow work with conditional distributions given the finite past. And it's not entirely clear how that relates to conditional distributions given the infinite past. So if you want to prove direct source coding theorems, you need some additional mixing type assumptions about these kinds of quantities. And it's a fact that if you have those kinds of assumptions, then you can in fact get matching second order direct source coding theorems for most reasonable codes. That is, they end up meeting the lower bound. So this is my summary of things that I need from information theory before getting into the talk itself. So as I said, the aim of this talk, we are motivated by networking concerns. So in the early 1990s, as we all know, there was this great empirical work of mostly, maybe some other papers. I'm sorry if I'm insulting anybody, but these are the two papers that I'm most familiar with. A paper of Garrett and Willinger and Beran, Sherman, Taku and Willinger, which analyzed variable bitrate video traffic coming from a wide range of codecs and showed, according to, I guess, semi-reasonable statistical criteria, that it has long-range dependence, although that's kind of controversial.
It was actually Walt Leland, right? First in the coding.
That's right. So you're right, actually. Yeah. So I don't know.
He first observed it, and then the others did some mathematics.
Yeah, you're right. His name should be in here. Thank you, John. Yeah. Any case, so this is what motivates us. And so what we asked ourselves is the following. Well, suppose that there's a source that's being compressed before it's being put on the net. And is the thing that is being put on the network long-range dependent because the source is long-range dependent, or is it something else involved? It's sort of loosely the question that we asked ourselves. So this is basically the focus of this talk is what happens if you have a long-range dependent process? Is it possible to actually compress the process in order so that the sequence of bits that you get out when you compress it can be short-range dependent? That's what we're going to talk about. So loosely speaking, our answer is going to be no. So, this is the philosophical point, is that you can't do it. Of course, maybe that will be false when someone comes up with a counterexample. So more precisely, what we prove is a precise theorem about long-range dependent renewal processes. And we precisely prove that the answer is no in that case. And in the process of doing that, we are actually going to make some general statements about countable state Markov chains, which are of more general validity. So that's the content of the talk.
Is there the constraint that Ln should be at entropy, or can it be?
Yeah, no, so we are, okay, that's a good point actually. So we are going to prove a lower bound with respect to the n times the entropy. So if you're already sort of messing up on the law of large number scale, then in a sense there's nothing to prove. In a sense, you're already sort of off on a completely different scale. So that's a precise statement. Again, the wording is maybe semantically can be argued with, but the statement is that the difference between Ln and n times the entropy has a certain lower bound. And if that's already on the scale of n, then you're okay, right? So, okay, so let's now get into the renewal process story. So we need some known facts. I'm not going to sort of prove the facts that are in the literature. So here there was a paper written by Daly in 1999 studying renewal processes with basically heavy-tailed interarrival times. And the fundamental theorem in that paper is the following. So let's take a renewal process with interarrival times having the distribution of t. Suppose that t has a moment index which is between 1 and 2. Then the renewal process has Hurst index, which is basically half 3 minus the moment index of the interarrival time. So what are these quantities? So the moment index is defined as the supremum of all kappa for which the kappa power of t is finite. Since t is a renewal process, then this thing has to be at least 1. And we're going to talk about long range dependent processes, so we're going to assume that the second moment of t is infinite. Now this is theorem is not general enough to cover the cases p equals 1 and equal 2. I'll say a little bit more about that later. So we're going to assume that p is strictly between 1 and 2. The Hurst index of an L2 sequence is defined as the value capital H, which is the smallest value of little h for which the running sum of the variances on the scale of n to the 2h. So in the short range dependent case, that would be capital H equal to half, because you expect it to be on the scale of n. So the theorem about renewal process that we'll appeal to is this one, due to Daly. Now we're interested in understanding data compression of these renewal processes. So as we just saw in the previous slides, the data compression is related to the behavior of the log of the conditional distributions given the infinite past. That should be a lowercase p, sorry about that. So we'll denote that quantity by rho sub n. So this is, you can think of this as a sequence of random variables derived from the underlying process, and it's a stationary process. So what we're going to show in this talk is that this is indeed an L2 sequence, and it has the same Hurst exponent as the underlying renewal process. So that's the main theorem really, as far as this the content of this talk, although it's derived from a somewhat more general theorem. So as we sort of already went through a somewhat careful discussion of Barron's lemma, so this in principle gives us second order converse source coding theorems. So I'm not going to sit down and prove these second order source coding theorems. It's mostly a matter of sort of drawing things from the literature where you have appropriate additional conditions that allow you to prove a lower bound in terms of a self-similar process with stable increments. There are many theorems of that sort around for processes that are sort of like the analogs of center limit theorems for processes that have Hurst index that is different from a half. So I'm not really going to prove that. That kind of go in that direction, but just appeal to Barron's lemma to say that one could do that if one worked harder. So the result really is the following. This is our main theorem. So if you have a renewal process with interarrival times having the distribution of t, which has moment index between 1 and 2, then there's a statement of Daly, and then there's a new statement which says that the rho sub n process, that is what's called the entropy density process, if you like, is also has the same Hurst index. So here's the proof idea. The proof idea is we start with the renewal process and we construct a countable state Markov chain from which both the original renewal process and the information density process can be recovered as instantaneous functions of the state. And then we go to a very nice paper by Carpio and Daly from 2007, which sort of discusses this scenario. That is, it studies countable state Markov chains which are stationary ergodic and have return times having infinite variance, and it sort of studies properties of instantaneous functionals derived from such Markov chains. We do have to do some work. It's not just a matter of copying things in the literature, so I'll tell you where the work is. But in some sense, we've got two functionals now of this underlying Markov chain, and so you might expect that they both behave the same way at the Hurst index level. So let me just tell you what the auxiliary Markov chain is. It's quite natural. We basically think about being in some state, and we look at the what precedes that state up to the most recent time we saw 1. So maybe I should get a pointer. Does it exist? Yeah. Oh, good. Okay. So just to get familiar with the notation for the rest of the talk, if you're currently at state 1 and your previous state was a 1, we'll call that state 0. That is, if the real process is at 1 and its previous value was a 1, we'll call that 0. We go through the even states, basically depending on how many zeros we have in between. Given that we are at 1, how many zeros we have in between before the previous one. So if you had just 1 0, that would be state 2. If you had 2 0, it would be state 4, etc. That's how we choose to index, just a numbering convention. And we go through the odd states if we happen to be at state 0. So if you're at state 0 and the previous guy was a 1, we call it state 1, otherwise we call it 3, 5, etc. Just some numbering convention that we chose to write the proofs down. So you can sort of, just to get familiar with this convention, since it's kind of important for the rest of the talk, imagine a particular sample of this process. So here's a 1 followed by 1, so that means that the auxiliary Markov chain is at state 0 because it has a 1, 1. Here it's like 0, 1, so it's in state 1, 0, 0, 1, it goes to state 3. Then you see a 1, so it's like 1, 0, 0, 1, so it becomes a 4. See a 0, it goes to state 1, etc. The red coloring there is for the even states. And it's kind of important because the even states behave very differently from the odd states. That's part of the difficulty of this chain. Basically, you enter an even state if you saw a 1, and as you can imagine, the probability of seeing that becomes smaller and smaller as you get more and more zeros, whereas the chance of seeing a 0 becomes closer and closer to 1 in the heavy tail case. So it's quite different behavior of this chain depending on whether you go along even states or along odd states. So now what we discuss is a problem that is actually a special case of what might be a more general question of interest for Markov chains. As I said, the Carpio and Daly paper is sort of focused on this question. So let's take now just some arbitrary countable state stationary ergodic Markov chain. And we are interested in chains of this type where the return times have infinite variance. So one result that is proved in the paper of Carpio and Daly is that if any return time has infinite variance, then all return times have the same moment index. It's not hard to believe that. You just have to go through the first step kinds of calculations. So it's proved explicitly in that paper. We'll take that for granted. So then we can sort of associate the concept of Hurst index to the chain itself. So we'll say that the chain has Hurst index h if any return time has index h.
Return time to what?
Return time to itself. So I mean, you start in some state, and any state, you start in a state and you look at the time that it takes you to return to that state, some random variable.
So you can bring regeneration, yeah?
Well, the chain is assumed to be stationary ergodic. So I can associate a bunch of distributions. To each state, I have the law of the return time from that state to itself.
It's explaining. So you start from the state at the return time.
No, I don't want to think about actually starting from the state. I just want to think of this as a bunch of derived objects from the chain. So there's a Markov chain. It's countable state, stationary ergodic chain. So to every state, I can associate a law, which is the law of the return time from that state to itself. So the statement is that every one of these laws, if any one of them has infinite variance, every one of these laws has the same Hurst exponent. I mean, that's not a non-obvious statement, but that's not too hard to prove. So our question is of the following type. When does an instantaneous function of a countable state Markov chain whose any return time has infinite variance, when does such a function have the same Hurst index as the chain? That's sort of the nature of the question. Because as I said, we're going to derive the x process itself from the chain. We're going to derive the rho n process from the chain. And if you can show that both of them have the same Hurst exponent of the chain, then they both have the same Hurst exponent, and we're done. That's sort of the logic of the proof. Now, this is actually a non-trivial question because you can easily construct examples where this is false. For instance, in the paper of Carpio and Daly, you'll see the following example. Rather easy to come up with, I think. You take a chain which has Hurst index, which is non-trivial. So return times have infinite variance. And another chain which is independent of it, which is basically a nice garden variety chain with finite variance return times. You take the product of those, consider a functional that depends only on the second chain. Well, it's still short range dependent, but the overall return times have got infinite variance. So you do run into issues like this. So it's kind of a non-trivial question.
So could you just remind me, what is the Hurst index of a return time?
The Hurst index was defined a few slides ago here. So the Hurst index of a process wait a second. So you're right. Actually, I think I did confuse you, didn't I? So I should have said moment index rather than Hurst index. You're right. Yeah. I'm thinking of moment index and Hurst index as sort of synonymous. Maybe that's what was Sergei's confusion also, possibly. Sorry about that. So I should have said moment index in the discussion of the Markov chain. Slides prepared on the plane, so excuses offered already. So I should have said here that every return time has the same moment index as every other return time. Thank you. But then, of course, the word we can still use the word Hurst index of the chain as being half 3 minus p, where p is the associate moment index. So to address this question, this paper of Carpio and Daly analyzes the derived processes from such chains. Now, I'm continuing to use the notation rho for these derived processes, but here in this statement, you can actually think of rho as being some arbitrary instantaneous function of the chain, not necessarily the rho that I'm eventually going to work with. So you can evaluate the variance of a running sum of such rhos, suitably normalized, and you can get this formula. It's not hard to write this formula down. You just have to write the products. When you calculate the variance, you get a product of sums, and so you get a bunch of cross terms, and you just gather the cross terms. But what's important is to understand the notation. So here's the notation that we are going to use for the rest of the talk. Our chain is assumed to be stationary ergodic, so it has some stationary distribution, and pi sub I will denote the stationary distribution of state I. So the Qijn are these running sums. It's sort of like the excess average visit times. So this is in stationarity in n steps. You get one copy of pi j at each time. This is the probability that you go from I to j in r steps. So you look at this excess return time. This kind of natural quantity. The r's are the running sums of the q's. So this is the notation that enters this equation. What you see on the right are a bunch of facts about these quantities, which is proved in this paper of Carpio and Daly. So remember that we have this heavy-tailed assumption, that is, the second moment of any return time is infinite. Under that assumption, it's true that every one of these Qij's will actually go to infinity as n goes to infinity. It's not hard to believe, it's true. Further, these r's will therefore go to infinity faster than n, because they're just running sums of the q's. What's kind of fascinating is that the r's are sort of all related to each other in terms of their asymptotic growth. That is, the ratio on a scale of pi j, rij over n goes to infinity essentially exactly like any other rijn.
If you have a good estimation for spectral depth, maybe you can write some simple equalities instead of long identities. Suppose you have spectral gap.
Spectral gap for what?
For Markov chain we are speaking about. So this whole potential series maybe.
Well, the chains I'm considering are long-range dependence. So we're not in the standard regime. Yeah, I mean, and these results depend on that statement, because otherwise you're not going to have this going to infinity and so on. And the statement about the equivalence of return times, blah blah, all that depends on this assumption. So this formula can be derived, and it's just a simple calculation. So as you can see, this is sort of like a sitting duck for the kinds of things you want to do with Hurst exponents of derived processes. So what's really going on is the following difficulty. You'd like to go to the limit as n goes to infinity on the left-hand side, while simultaneously doing that on the right-hand side. So you want to address this question. Is it true that this limit on the left is actually what you expect to see on the right? Because these things pointwise, they go to 1. That's really the meat of the talk, so to speak. I mean, why this is not just a matter of copying things from the literature. So exchanging the limit in n with the sum over I and j is not trivial. In fact, it's false. For instance, if you took a constant function on the chain, then this exchange of limits does not hold. So the reason for that is that the convergence of these ratios is far from uniform in the pair ij. Because you see the rijn involves a qijn. The qijn are running sums of pijn minus pi j. And if j is very far away from I, so to speak, you don't get any chance to get to j. So you have these deep negative excursions, which for a countable state chain depend on where you start. So you get this non-uniformity, and you've got to somehow deal with that. So most of the work is really in figuring out a way to get the appropriate uniform integrability condition when we do the following. We view these quantities, that if we think about rho I times rho j, remember at this point rho is some arbitrary function although eventually it's going to be this log density that we talked about. We view it as a function on pairs ij having the product distribution pi I pi j. So you can think of these as random variables relative to this probability space, and we need to prove a uniform integrability condition for that. That's really where the work is, and we do it essentially by a trick, by focusing on the right thing. But as usual, as in all these things, it takes a while to figure out what the right thing to do is. So as you know, in mathematics, everything is impossible until it becomes trivial. So after you do it, it's trivial. So this is what you need to do, and what we prove is the following general theorem about countable state Markov chains. This is true for any countable state Markov, stationary ergodic countable state Markov chain with return times having infinite variance. That is, you have this absolute summability result. So proving this requires has an upper bound part and a lower bound part. You can think of this as corresponding to the uniform integrability result for the functions rho I, which are exactly equal to 1, so to speak, right? And this requires an upper bound and a lower bound. So for the upper bound, we start with a standard identity. So the property of going from I to j in r steps is the property of going from I to j without visiting 1. So this is taboo probabilities in the usual sense of, say, the book of Chung on stationary Markov chains of stationary transition probabilities. So and the other way of doing it is you go from I to 1, then you go from 1 to itself a few times, and then you go from 1 to j without visiting 1. So this is standard identity, and if you work with this identity, you can easily prove the following inequality, which is that the qijn's on the scale of pi j are basically like the q11n on the scale of pi 1, except for some correction terms. The correction terms don't matter too much. If you think that through, you'll see that they sort of don't matter. And now, when you work with this, you could sort of go to average. If you're interested in the average of this left-hand side over pi I pi j, and likewise on the right-hand side, actually, if you're interested in the average of the running sums over n of these quantities, which were the r's, so you're somehow forced to deal with this corresponding average for this correction term, and that turns out to be on the scale of r11n. This is not so terribly hard to see, actually, since you're summing over j. When you sum this up over j, it's like looking from the property of going from I to some place, some arbitrary place without visiting 1. So that sort of leaves behind the probability of visiting 1, and then you can see that that's being summed up over on the average over pi I. So that's like the stationary version of that object, and then you sum up over n. So you can sort of believe that you're going to end up getting something like this. But I'm not going to bore you with the algebra, it's all in the paper. So then you have to divide this whole equation out when summed over n, divide it all out by r11n. And since the r11n over n is going off to infinity, this term doesn't do much problem. It doesn't cause any problems because it's increasing like n when you sum this up. So when dividing by r11n, it sort of disappears. And when you divide this out by r11n, you get something which is finite. Basically, it's 1. So you get these things sort of controlled. This is how it gets controlled from the upper side. Now, what is really fascinating is that we expected more difficulty on the lower side, because the lower bound looks a lot more challenging because of these deep negative excursions that are possible in a non-uniform way on these ratios. But the term that was causing that problem ended up very conveniently just vanishing if you did things right. That's because you've got this cancellation. When you average over pi I pi j, these terms, you're basically just getting 0. That is, the average excursion when averaged over the appropriate measure just disappears. So this is sort of what controlled the lower bound. So this gives you some sense of how that result was proved. And now I can state a general theorem for instantaneous functions of.
When you stated the theorem there, you
Yeah.
had as an assumption this infinite variance thing.
Yeah.
Where does it get used in the?
Well, it gets used for instance, in saying that r11n over n is going off to infinity. When we divide by r11n, we need to control this term, for instance. When you sum this up over as a running sum of q's, you get something which is proportional to n. When we divide through by r11n, that needs to sort of disappear. Yeah, because otherwise it might sort of stay, it might increase and doesn't give you a finite right-hand
The
side.
thing about the ratio,
Yeah.
that bullet point, that's just the Chicone-Ornstein ratio-ergodic theorem, right? The result that you had
Which ratio?
back earlier.
Yeah, the thing going to 1.
Yeah, the thing going to 1, right?
Yeah.
That's sort of just something, that happens kind of, for any recurrent kind of chain, isn't it?
Yeah, I mean, it's possibly true, but there are a lot of things that are going through this calculation that depend on this statement, and I'm sort of focused on entirely the use of that statement. So I haven't really thought through the analogs in the...
No, I was just trying to figure out where the assumption and variance.
Yeah, I mean, in the context of this proof structure, it shows up in trying to get this term to vanish, and that is not something that will go away in the short range case. But what you're suggesting, I think, is that it may be possible to do an alternate proof.
No.
Okay.
I was just sort of saying some of these facts don't depend.
Yes, of course, yeah, right, yeah. But I mean, we're just so totally focused on that for this talk that it's not a direction that I've explored. So certainly wouldn't want to do that in real time. So here's a theorem about instantaneous functions of Markov chains, of these kinds of Markov chains, that is stationary ergodic chains. Now we're going to order the states in some way. So you can think of the state space as being just the natural numbers, and we can make the following statement as a consequence of that absolute integrability result. Take an arbitrary function of the state space, which is a finite variance under the stationary distribution. Suppose that as I goes off to infinity, remember that we've ordered the states of the chain, these instantaneous functions converge to some limit mu, and mu is not equal to the expectation of this function. This is very important. Then you can conclude that rho has the same Hurst index as m. Point being that you already have the absolute integrability result, and therefore these quantities are basically bounded in absolute value. So you can just apply that result directly to get the uniform integrability you need. But the limit will be non-zero only if the average of the rows is not equal to mu. Otherwise, you're just getting a 0 and you conclude nothing about the Hurst index. So as long as you're not sort of converging to the mean, you're okay. So that explains the case with constant functions. Constant functions, you are converging to the mean, so you can get bizarre behavior. So this is a general theorem about Markov chains. So this actually proves our result that you get the same Hurst exponent, because you can do this. For instance, now let's go back to rho being the log of the conditional probability given the infinite path, and you take another possibility for rho, which is the indicator that you're in some particular state. Now, when divided by these things, they're basically giving you non-zero limits, so they both have to be on the same scale, and we already know that this is on the scale of the Hurst exponent, so the other guy must be on the scale of the Hurst exponent. That's sort of how the proof ought to go, except I have 15 minutes, so we're not done. So thing is, let's try to do this for our renewal process. So here's the auxiliary countable state Markov chain associated to that renewal process. You can explicitly write down all the quantities of interest. So for instance, how do you figure out the stationary probabilities? Well, the renewal process is stationarity, and the states were defined in terms of the preceding of the past. So you just want to look backwards, and you can figure out what the stationary distributions are in terms of the stationary renewal distribution. So you just write down formulas for the stationary distributions. As for the function that we're interested in, it's a log of conditional probabilities. Oh my God, so I've lost. Okay, that goes around. Thank you. So this is, for instance, at 2k minus 1, you have you're sort of going through the odd states. So it's a question of whether you haven't yet seen a point. So you get a conditional probability that looks like this. You take its log. For the even states, you're looking at the chance that you actually just finished the current period, and you get probabilities that look like this. So as you can see from this, this behaves quite differently from that. So if you look at an expression like this, and you play around with it, it's relatively easy to show that this rho function is indeed a second moment function, because you sort of see things that look like x log squared of x, and that has a uniform bound. Done. Okay, it's not so hard to do that. So let's try applying this now to the garden variety renewal process. For instance, a basic renewal process having a given moment index would be something whose tail properties of whose interarrival times behave like this for some slowly varying function. And you can just explicitly compute the rows in this case, and you see that they go to 0 when moving through the odd states, but they go to infinity when moving through the even states. So you try to enumerate the things and apply our theorem, you can't do that because you don't get a limit, right? So theorem is not good enough, even for this basic example. So all right, so you've got to work a little bit harder. And here is the harder theorem, so to speak. I mean, just sort of make things work out for what we want to prove. Again, there are no statements about this being the final word or anything like that, right? I mean, there's lots of scope for getting better answers. So we just sort of make the right assumptions that are enough for us to deal with the original question we were interested in, which is the question of the Hurst exponent of this of the entropy density process. So what we want to do is we want to isolate some kind of bad set where the limits are not behaving the way we would like them to behave. So we take, again, this is a general theorem about arbitrary countable state Markov chains with return times having infinite variance. To take any such Markov chain, stationary or ergodic, suppose that there is a subset of states, and we think about the states as being enumerated because we want to apply our earlier theorem. So suppose there is a subset of the states which we can now think of as being the natural numbers, where this kind of bad term, remember this was the bad term that showed up in the difference between the qij's on the scale of pi j and the q11's on the scale of pi 1. We would like that bad term somehow to not matter. So we want for the centering of the rho function around the thing that we would like it to converge to, on the set that is bad at the appropriate scale, because things get essentially going to get divided eventually by r11n, so on a per letter basis we should be dividing them by q11n in effect. On the appropriate scale you want to get uniform integrability, so we just assume that that's with respect to the pi I distribution, and we would also like this average to actually go to 0 as n goes off to infinity, so we just assume that. So what we want is actually as the state space is enumerated, so we take big chunks of the state space, and the portion that is in the bad set, the portion that is not in the bad set and outside these big chunks is converging the way we want, and then this comes from our original theorem. So if we put all this together, then you can prove that rho has the same Hurst index as Mn. This is not so hard to see because we just made the assumptions we need in order to prove this. So now you can apply that to the renewal process, and you go through the calculation, and we can in fact prove our theorem for arbitrary renewal processes, provided that the distribution of the stationary renewal time has finite entropy. And because we're working in a regime where the moment index is strictly bigger than 1, this is automatic. So it's not really an additional assumption. On the other hand, if you were trying to be more ambitious, then this would look like an assumption you might want to try to get rid of. Now, on the principle that every talk should have at least one result that is not proved, I'm not going to prove this result. But it has some calculations, because I sort of give you proofs about everything else that exists. But it's just a calculation, and this is what you get out of this. Besides, I don't have the slides for it, I might have had time. So I'm almost done. Here are some generalizations that one might think about. So we've studied only renewal processes, and our theorem may be able to handle actually broader class of processes, etc., because it's more general. Most interesting, perhaps even in the context of renewal processes, is what happens in these boundary cases where the moment index is either 1 or 2. I don't think, actually I'm not entirely sure what the statement in Daly's 1999 paper is exactly saying. I need to think that through. It's certainly true for the moment index between 1 and 2, but it's possible that there's enough technique there to tell you some things in the boundary cases also, but not entirely figured out what that is. In any case, the finiteness of the entropy of the renewal time distribution seems to enter our proofs, and if you don't have the moment index strictly between 1 and 2, it would be interesting to see whether that can also be got rid of, etc. This is some natural questions just along these lines. Okay, now anybody who works in information theory is going to say, well, in practice nobody really does lossless data compression. You're sort of only interested in compressing things to the extent that they are good enough. Certainly for images and all that, you don't want to be perfectly lossless. So you might ask yourself whether when you do things like lossy source coding, you've got to sort of map that into this framework somehow, do you still have this property? Do you still have the Hurst exponent not suddenly becoming nice? Or is it possible perhaps that if you gave up enough on distortion, you could somehow erase the long-range dependence? You know, that's a conceptually interesting question. So that's something we have not considered. And what we've really proved is a general theorem about functionals are countable state Markov chains. We just used it to illustrate a particular kind of question, but you might be interested in other kinds of questions, so this theorem or other kinds of theorems might be interesting. So I'm done.
Venkat, you talked about prefix-free codes only, which so low, so long-range dependent, you cannot destroy them. But can you look at the larger class of codes for which you can actually destroy?
Yeah, so I think the third question I raised is along those lines, which is the rate distortion story. But any place you have Baron's lemma, you're basically doomed. And I suspect that if you're, I'm not sure of exact formulations, but if you're doing something that has got the entropy sort of sitting in it, there's got to be some version of Baron's lemma that is going to lead to the same kind of connection between the log entropy, the entropy density and the coding.
But Baron's lemma applies only for prefix.
Well, the way I stated it, yeah, but what underlies it is far more natural. It's a very natural thing. Right? Somehow the entropy is sitting like this elephant that you have to carry along, so you can't get away from it. I suspect that you'd be able to find whatever you came up with, unless you were willing to give up on compression, you'd be able to find an analog of Baron's lemma that would make the same process go through.
So on the boundary case, when p is at either 1 or 2, but consider the case when p equals 2, then your Hurst pattern is exactly 1/2.
Right.
Is that still non-independent, or is, for example, like the fraction of running motion and the standard running motion we have h is equal to 1/2. So just wonder for the p equal to 2 case,
Yeah.
whether you still have that.
Yeah, so I mean, as I said, I've not really got a clear enough picture of the proofs in Daly's paper to find what is being said about the case p equal to 2. So it's basically a subtle question, I think, and I don't know offhand what the answer is. Maybe Sergey knows.
No, it's just from both directions. So
Yeah.
either the second moment exists or not. First.
No, you have to assume that the second moment does not exist.
Yeah.
Because that's a standard definition of long-range dependence. But you could be in a scenario where you're sort of coming at it through finite variance objects, and then what does that mean for the Hurst exponent, right? Because the moment index is 2, so you've got a finite variance for every kappa which is less than 2, but at 2 you get infinite variance. Now, what is the Hurst exponent? That's a different mathematical object in terms of the growth rate of the variance. And if you go through Daly's proof, there's a little epsilon that enters those proofs, which requires you to be a little bit away from 2. But if you think it through, maybe you'll be able to make the proof work. All I'm saying is we haven't really figured that out, and apparently the experts haven't either. So that's the state of that situation. Yeah. And there's a similar question at 1, right? Because you could sort of immediately become infinite variance when you go away from 1.
For equal to 2, you still have infinite variance?
Yeah, the standard definition of a long-range dependent renewal process is that the second moment be infinite. But the moment index in that case could be 2. And also for the renewal process to exist, the first moment has to be finite. But the moment index could be 1, because the moment you get away from 1, you might get infinite variance. So those are the boundary cases where the picture is not entirely clear to me. But the theorem that is in the literature and correct is that when you're strictly between 1 and 2, then you have the equivalence between the Hurst index and the moment index in effect.
Any other questions? Okay, if not, let's thank the speaker again.